Hey, Mr. Geraci, this is my video for the distance learning assessment on rational functions, and in this first part here, we will be graphing a rational function, as you will see now. Hello, welcome back. In the function that I've chosen for us to graph right here is this, x minus 2 over x squared minus 2x minus 8. And well, the first step here, as with any other function, would be to determine if we can actually make factors of any of the of either the numerator or the denominator. Now, if we look here, the numerator is already as simplified as it can possibly get, but the denominator can be factored out. So if we factor out the denominator, it can become x minus 4 x plus 2. So our new equation, or our new factor, will look like x minus 2 over x minus 4 x plus 2. This one right here. And this will be the basis for pretty much everything else we do in the problem for when we figure out how to actually graph it. Now that we've our factored out problem here, we can determine the vertical asymptotes, which are pretty much on the graph where it sort of gets divided into different sections, where you have lines that go all the way up to infinity and all the way down to negative infinity, and it really looks like the graph is being split into sections. So the way to determine these is by setting the denominator's factors to 0 and then getting what the x is equal. So here x minus 4 equals 0, which would mean that x equals 4, plus 4 plus 4. And then the other one would be x plus 2 equals 0, minus 2 minus 2, x equals negative 2. So our two asymptotes are 4 and negative 2. And these will be the points on the graph where it actually looks like it's being divided into sections. So this is very important for later. The next step for us to do, which is actually really simple in this problem, is to determine the horizontal asymptote, which is when, because our graph will probably look like this to some extent, it's where the lines won't cross, kind of where they stay in their own sections. So we have to kind of determine where that is. So you determine the horizontal asymptote by looking at the coefficients of the numerator and denominator. And because each of them have a hidden or invisible coefficient of 1 here, there's none. The horizontal asymptote is just 0. So on our graph, when we actually graph it, these sorts of sections won't cross the actual line here. They'll be in their own areas. Now, this isn't true with all factors, with all functions that you graph, but in this case it is. In other cases, for example, you might have 2 x minus 2, if that was a possibility. You'd have the horizontal asymptote be 2. And then you might have a section here that goes all the way up here, to like 1.999, and the other that goes all the way to 2.00001, but it'll never actually reach the line itself. In the previous section, actually, I might have accidentally lied a little bit. The outlying lines here, the ones that kind of go like this and this, they will never cross the horizontal asymptote. But in some cases, for some of these functions, you'll have this sort of middle line that does. It's sort of its own thing. It's going to be between the vertical asymptotes, but this does cross the horizontal one. So in order to determine where it crosses the horizontal one, we need to find the 0 of the problem, which is pretty simple. All you do is just take the numerator and set it equal to 0. So x minus 2 equals 0, plus 2 plus 2, x equals 2. This means that in our problem, the middle section, when we graph it, will cross the horizontal asymptote at 2, right here. So we know where that's going to happen, which again, pretty useful when you're graphing. You could technically solve all these things just by inputting your points into the problem itself, though that might get confusing, since if you have one here and here and here and here, You might make some false assumptions if you just put them in. You might say something like this, which would just be totally incorrect. So it is pretty important you actually calculate these things out. So now what we're going to do is actually start to put some of the stuff onto the graph. So we know that the horizontal asymptotes are 4 and -2. And because I had to redo this scene, they're already on the graph. How convenient. So here's this one, here's 4, here's -2. And all the actual lines, the individual ones, will kind of be confined within these 3 sections. We'll have 1 somewhere here, 1 here, and 1 here. They cannot, at least with this function, in some other functions they can, but here they will not cross this. The horizontal asymptote, as we already found out, is 0, which is pretty much already here. The middle line, though, will cross the horizontal asymptote. We know that the x-intercept there is 2, so we already have 1 point on the graph. For us to actually be able to figure out what it looks like, though, we do have to calculate some things. So we can get the original equation, or the factored form, actually. So x minus 2 over x minus 4, x plus 2. And then we can start plugging in some of the numbers here to determine what it looks like. So let's put in 0, for example. So 0 minus 2 over 0 minus 4 times 0 plus 2. So -2 over -4 times 2. And this, the denominator will come out to -8. -2 over -8 is 1/4. So at 0x, so 0, comma, 1 over 4. We found another value here. So 0, 1/4. So we know it's going to do this. Probably connects there somehow. Oh, we'll have to see how. So we should start plugging in some more of these. And you can plug in as many as you'd like, but at least a few per each section would be good. So we could do another one here like 1. So 1 minus 2 over 1 minus 4, 1 plus 2. So this would be -1 over -3, 3. -1 over -9. This is what we kind of calculated once we put in 1. So that'll be 1/9. Here we can graph that, which would be 1/9. Jeez, and I'm putting in 1? Oh, that makes sense. Never mind. It's a bit weird looking at this since it's upside down for me, but that does make sense. It kind of goes down here since we put in 1. We could do -3 now, since that would provide some valuable insights into where this kind of goes. So -3. -3 minus 2 over -3 minus 4, -3 plus 2. So -5 over -7, -1. This would be -5 over 8. So -5/8 is what this one, what 3 comes out to. So -5/8, that's about halfway, like here. So we can start to see sort of line emerging here, like this. So it seems like if we put in 1, or excuse me, -1. If we put in -1, it'll probably be here. Then we can start to actually form out the line itself. So let's put in -1. -1 minus 2 over -1 minus 4, -1 plus 2. So it'll be -3 over -5, 1. So -3 over -5 is just 3/5, which, you know, getting closer to fully 1. So it's like that. And you don't have to do all these decimals and things. We can assume that it will do this. That's the kind of... that's what we've gotten from putting in these. You can start to see this line clearly develop, and it has to stay within these boundaries, so it's going to do that. We can do the same thing, though, with these sections here. So once we find one that's outside of these boundaries, we can determine it. So -3, for example. Just get a new piece of paper. So let's put up the original one, x minus 2 over x minus 4, x plus 2. This is our base problem. Let's put in -3. So -3 minus 2 over -3 minus 4, -3 plus 2. So that would be -5 over -7, -1. -5 over 7. -5 sevenths for -3. So -3 is here. -5 sevenths would put it probably about here. Yeah. Yeah, okay. It's just, again, confusing. We'll get this backwards. We could do -4 now, see where that goes. It'll probably be here. Since we're already in here, we know it's kind of going to look like that. -4 should be somewhere over here. But let's put it in just to make sure. So -4 minus 2, -4 minus 4, -4 plus 2. So it'll be -6 over -8, -2. -6 over 16, which simplifies to -3 over 8, which conveniently works out like this. So again, we can know that it will go like this. It's going to kind of mirror itself, so if you're really tight on time, you could just invert this to be here, but since we have as much time in the world as we could possibly ever want, we'll calculate a point here just to make sure that it's actually in this quadrant. So let's do, what would that be? 5? Okay. So 5 minus 2 over 5 minus 4, 5 plus 2. So that's 3 over 1, 7. So 3 over 7, 3 sevenths, which, would be here. And conveniently, that works out well. So we know it's going to go like this. It's in the right quadrant. Like that. So this is what our graph looks like. You could do this in as much or as little detail as you'd like, but you do generally need a few points in the middle, at least a couple in one of the quadrants, and if you want to be safe, a couple in the other quadrant as well. With this, though, we can actually start to find out the domain for this. And yeah, we'll talk about that in the next section. So what we need to do now is figure out the domain of the graph, which is basically where each section goes up to. And you do this by starting off with negative infinity. Since it's coming this way, you go negative positive, boom, you hit -2, and then you get to the vertical asymptote here. So -2, comma, negative infinity, comma, -2, close parentheses, v, another parentheses. Now you've stopped here. The v sort of signifies that you're now in a different area, like the range has changed. So we're starting at -2, going towards the positive, so -2, again, comma, and you can keep going here, boom, until you hit the other vertical asymptote, which is 4. So -2, comma, 4, because that's as far as you can get in this section. And then, just like the first, you have v again. You start off here at 4. So 4, comma, and there's nothing blocking you for the rest, for any other number after this. So 4, comma, infinity. So this is what your domain is going to look like. So negative infinity, comma, -2, v, -2, comma, 4, v, 4, infinity. So this shows how large, where each section on this graph goes to. So one goes from negative infinity until negative 2, the other negative 2 to 4, the other 4 to infinity. And this is really the last step of what you need to do, because you've graphed it, you know how large each area is, you have points on here, and that is how you graph a function. So thank you for watching this, and I hope you'll enjoy my next videos on similar topics. Hello again, Mr. Geraci. I bet you realize how long that first video took. 15 minutes of watching. I think I might want to cut down a little bit. I'm still going to be descriptive, but this second video will be a bit shorter. This video is about simplifying rational expressions when dividing. Now there's less to talk about here, there's less things for us to go into, so it will be a bit shorter, but you know, I'll be in depth with it. It'll still maintain everything we need to know. So I hope you're ready. And we're going to be explaining these rational functions that we're going to divide now. So we're back, and the problem that we will be simplifying and, you know, make it better is x squared plus 8x plus 15 over x squared plus 2x minus 3 divided by x squared minus 25 over x squared minus 5x plus 4. Now, the first thing we have to do here, even before we simplify or factor out the numerators and denominators, is we have to change this to become multiplication and switch these. So our new problem that we will factor everything out of will be x squared plus 8x plus 15 over x squared plus 2x minus 3, same first section as before, multiplied by x squared minus 5x plus 4 over x squared minus 25. Now, it is necessary that you change this to multiplication and you flip it over, because if you don't, it'll be impossible to really simplify anything. I mean, of course you'll be able to factor it out, but that's as far as you'll actually be able to go. Here, though, we're actually going to be able to find a fraction at the end. Like, that's the goal of this, not just to come up with what, say, x squared plus 2x minus 3 is. We need to find out what this whole thing becomes, and this is the way to do it. Now that we have switched this second fraction over, though, and changed to multiplication, we can start to factor stuff, which is the next step. So the top expression here, x squared plus 8x plus 15, will become x plus 3 times x plus 5, since these add together to get 8, multiply together to get 15. This will all be over x plus 3, x minus 1, because x, well, 3 and negative 1 add to 2, 3 and negative 1 multiply to negative 3. So our first expression. Our second expression will simplify out to x minus 4 multiplied by x minus 1, because negative 4 minus 1 is negative 5, negative 4 times negative 1 is 4, and the bottom expression, the simplest of them all, x plus 5 multiplied by x plus 5. Pretty self-explanatory. Or, excuse me, x plus 5, x minus 5. Yeah, that was a close one, since 5 times negative 5, negative 25. X times x is x squared. 5 plus negative 5, 0. So you don't have that. That's why you don't have an extra expression here. It gets canceled out. But this is our new our new factored form of this. X plus 3 times x plus 5 over x plus 3 times x minus 1 times x minus 4 times x minus 1 over x plus 5 times x minus 5. Now we can actually start to cancel some of the stuff out, since we did switch it before. We can do, well, there's some obvious ones here. X minus 1 cancels out with this x minus 1. What else? There's x plus 5 here. This cancels out with this x plus 5. And we can also cancel out these two x plus 3's as well. Now, we've canceled out a lot here, but this is really what you have to do, since this will give us a fraction. This will give us our simplified answer to it. Now, this whole first expression is gone. And these two are gone as well. So what we're left with is x minus 4 over x minus 5. This is our answer. Because we switched the two fractions before, made them a multiplication problem. We factored out each of the individual components, and now we're able to cancel them out to get this answer. This is a pretty versatile thing. You could use this for any sort of problem where you're dividing factors, but this is just a good example since it's not overly complicated, and what you learn here could certainly apply to others as well. So, thank you. I know this is a bit of a shorter one, and we'll get back on video 3. Hello again. So this is the third video. It'll be about simplifying a rational expression when subtracting. Yeah, I hope you'll enjoy. And here we are now. So the complicated seeming rational functions that I've chosen for us to subtract are 2/3 x plus 7/3 over x plus 5 minus 1/5 x plus 2 over x minus 3. And yes, this does seem very complicated, but the best thing to do here is you need to have common denominators. Here we don't. And the best way to get common denominators is just to multiply the denominator of one side alongside the other on the other side. So what we'd have now would be x plus 5, x minus 3 here. This will be our new denominator for both. So on the top here, we multiply everything by x minus 3 as well. So it would be 2x plus 7 over x plus 5 times x minus 3 minus x plus 10 over x plus 5 x minus 3. And now that we've done that, we've gotten a much simpler subtraction problem for us to solve. What we can do now is just, because they do have common denominators, they're pretty much the same, we can just put these together. Make them one. So 2x plus 7 minus x plus 10 over minus x plus 10 like that over x plus 5 x minus 3. Because they have the same denominator, we can put them together. They have now one numerator, so we can simplify this. It's sort of like the division one, but a bit less complex since it's only dealing with addition and subtraction. The same rules do apply for this as they do to addition as well. So our newly combined fraction here, 2x plus 7 minus x minus 10 over 5 plus x times x minus 3, we can simplify the numerators. So, just adding them. So here, 2x minus x, just x. 7 minus 10 is negative 3. So x minus 3 over x plus 5 x minus 3. Now, this is a whole lot simpler than what we had to start with, but this is not the end. We can simplify it one step further. Because we do have a shared numerator and denominator here, we can cancel that out. And then we'll get the answer to our seemingly very complicated original problem, which is just x plus 5. That's it. Because we got rid of the components that are shared. We just combined everything into one, and the parts that are the same just poof, go away. This is, the value that was obscured by all these fractions and such originally. But just by making sure that everything has common denominators and combining them, we can get these answers pretty easily. Same thing works for addition, as I said before. So yeah, this will probably be very useful, even more so than the other two, especially in uses outside of just Algebra 2. And though you do have to have common denominators, you cannot do any of this without them, because even if you have these shared components, I suppose, if the denominators are not the same, it doesn't matter. You won't be able to solve it correctly. But because we were able to find easy common denominators, we got that shared problem, and we got one solution. So I hope you liked this video, and we'll be coming back with our last video, video 4, right now. Hello, Mr. Geraci. We're going to be solving rational functions in this video. This is video number 4, the last one, and I hope you'll enjoy. So the rational function that we're going to be solving is x plus 2 over 3 equals x3 minus 2 over 6. Now this isn't too hard of a one. Obviously there are other options you could do, but the general things we're going to cover here and how to solve this can be applied to other ones as well. So first of all, you want to get rid of these denominators. And since there's no variable in the denominator, it doesn't have to have a common denominator. You can just get rid of the denominator. And that's done by multiplying. So here goes to here, so 6x plus 12 over 3 equals 3x minus 2. Because we got rid of this, we multiplied it here, and now we do the same with the other side. So multiply by 3, 6x plus 12 equals 9x minus 6, because in order for this to just be the numerator, we multiply it by 3 to get rid of the denominator, but this side must be multiplied by 3 as well. So this became, 9x minus 6, and once it's all here, we have this. Now, just using simple algebra, or algebra 1 skills, we can solve this quite easily. So minus 12, minus 12. So 6x equals 9x minus 18. That's the sort of half-solved form. But here we can subtract 9x minus 9x on both sides. Negative 3x equals negative 18. Like this. So divide by negative 3. That gives us x equals 6. Because, we had the fraction, but we got rid of the denominators by multiplying. We had the combined equation where we did multiply them, and we were able to just simplify everything out and add things to both sides for it to be a single answer. Now, there are other more complicated equations you might get where you have to have the greatest common factor. For example, if there was something like 3... okay, this is a theoretical one. I'm not sure if there is a real answer, but 1/3 plus 2x over x, or actually, let's do 2x squared over x, equals 2/3. So here you'd want to multiply everything by 3 plus x, so it would cancel out here on this side, and then this side would get that in the numerator, because it just covers most of the equation. It covers more than you could just by doing a single one. This is by far the simplest. There's really not any specific things or special tricks you need to know. Only that, you have to just find an adequate greatest common factor and factor the numerators or denominators depending on how complex they are. Because if it's in an unfactored form and you try to just take out greatest common denominators and things like that, you'll probably get answers that aren't right simply because you didn't factor it out. But once you factor it out and you can find these greatest common factors, it becomes fairly easy to solve to get what the x actually equals, because this is fundamentally, after the factoring and greatest common factor, it's algebra 1 type math. So it isn't too hard, definitely used in other places as well. Used in other fields, other maths, probably other equations and things we're going to be doing next unit. But anyways, I hope you enjoyed, and we'll have a little recap video with me at the end. So here we are. It's been a good half hour of, well, watching time for you, I'm sure. It's been definitely more than a half an hour for me, and I'm glad to be done with this assessment. I suppose I could throw in a couple remarks here, though I would like to say there was a mistake that I made that I realized in the first video. When I was graphing out the function and I was putting in points, I said 3, but I calculated it for -3, which gave me an incorrect answer. The answer I got for what should have been x3 was -3/7, which was actually the -3 point. The correct answer should have been -1/5. It looked right, and it was upside down for me when I was actually recording that part. So I got the positive and negative confused there. But it's still... it didn't mess things up too bad. I didn't notice it while I was actually recording. In terms of Zoom and things like that, I suppose just throwing a couple remarks here. I feel like assessments like this definitely work best. The practice test that we had to do on OneNote is considerably more difficult than the ones we did in class for me, just because I don't have any way to really write on the screen. So anytime I have to actually put in like a formula or an equation, I have to type it or use my mouse to draw lines, which is very sensitive and doesn't quite work very well in OneNote Online. So I would say that videos and things like this are much easier rather than doing full-blown tests, at least in the traditional way. I know some of the other classes have done like forms and things like that. I think those work well too. But yeah, that's kind of my views on it. I feel like it's a good amount of work. This assessment didn't take too long. It obviously took longer than half an hour for me to make this video, but I would say it's not bad compared to what I would have expected, especially for a unit test. So yeah, I hope you enjoyed. I obviously hope I explained well enough, and hope you stay safe, stay healthy. See you when we go back to school eventually.